Hello, everyone. So in 1993, the National Center for Supercomputing Applications, or the NCSA, which was then a unit of the University of Illinois Urbana-Champaign, released something that you may have heard of called the NCSA Mosaic browser. It's the first popular graphical web browser. And it played an important part in the development of what was then a very young World Wide Web. So in 1994, a company in Mountain View, California called Mosaic Communications was born. So they hired a lot of the NCSA folks to go and build a completely different browser. It didn't share any other code with the NCSA Mosaic browser, and they called that browser Netscape. So the internal code name for the browser was Mozilla, which was a portmanteau of Mosaic and Godzilla. And the first version of their web browser, which was called Mosaic Netscape, and the version that they released was 0.9, was released in 1994. Within about 4 or 5 months, it had taken 3/4 of the browser market, which admittedly at that time was much smaller than it is today, and it became more or less the main web browser for the bulk of the 1990s. To avoid a trademark problem with the NCSA, the browser was then renamed to Netscape Navigator, which is the name most people know it by, in the same year. And then that company became, instead of the Mosaic Communications, became Netscape Communications. Now, at this point, web browsers could really only render files. It was as if the web were a series of static PDFs, and you could just look at the PDFs that somebody else had already made, but that was about it. So Netscape Communications realized that the web needed to be more dynamic and was going on a path towards being that. If you had this sort of hypertextual, highly resource-oriented world, why wouldn't you try to build a more dynamic web on top of that? And Mark Andreessen, who was the person who founded Mosaic, thought that HTML needed to have a glue language that was easy to use by web designers and part-time programmers to assemble components like images and plugins where the code could be written directly into the markup. And in 1995, Netscape Communications recruited Brendan Eich with the goal of embedding a programming language into Netscape Navigator. So at the time, they thought that programming language was going to be Scheme, which is the logo you see there. But before he could get started, Netscape Communications collaborated with Sun Microsystems to include Sun's more static programming language. Scheme is very dynamic. It's very object-oriented, very oriented around message passing and things like that. So Java doesn't really look like that, but Sun Microsystems thought that that would be, because it was more mature at the time and they were sort of framing their architecture around that, they thought that that might be a better way to compete with Microsoft for user adoption of web technologies and the platform as a whole. So they said, forget about Scheme, let's use Java instead. And so Netscape Communications then decided that the scripting language they wanted to use in their first web browser was something that would complement Java and should look roughly like Java. And so they stopped adopting Scheme and some other things that they were considering at the time, which is why JavaScript looks a lot like Java and has Java in the name, right? And so to defend the idea of JavaScript against competing proposals, the company needed a prototype. They had to sort of spike this and make sure that it worked. And Brendan Eich wrote one in about 10 days in May 1995. So when you write a programming language and you ship it to production in 10 days, it may not have all the features you might think of in a typical programming language. And in fact, when you look at the release notes for JavaScript 1.1, which is the release that immediately followed that one, you can see what they left out in the first one. So we didn't have arrays or booleans or functions or numbers, didn't have nan, new operators like typeof and void showed up. There was a new piece of functionality where math.random didn't return 0 all the time. It seems like an important feature. And you could delete objects. Nevertheless, despite this, a little bit of despite that sort of rapid start, it was very successful, right? The adoption of Netscape in the 90s was enormous, right? The market share here is tremendous, and it was only after Microsoft started making inroads that that's eroded that market share a bit. And so today, every browser ships with a JavaScript engine. This is a rousing success story, if you want to think of it that way, for the digital age. But not every kind of code we might want to run on the web is a good fit for JavaScript. So one problem is that JavaScript's not a runtime, it's a language specification. So each of those browsers has a different low-level representation that they run that JavaScript. So Chrome uses an engine called V8, Firefox uses an engine called SpiderMonkey, et cetera. And unlike JavaScript, there's no specification about how those different engines should be written. So they're free to use whatever low-level internal representation is of value or interest to them. But that means that we can't take some other language and make it target the JavaScript runtime in a cross-platform way without essentially compiling to JavaScript first. And that means that we can't really bring in some of the other ideas that have been happening in programming languages and the way we structure our software that have evolved in the last 25-ish years. So for a quarter century, you have not been able to take stuff that you wrote that wasn't JavaScript and put it into a browser without turning it into JavaScript first. It's not a very efficient way to do things. When you look at other kinds of runtimes, that's not true. So if you look at, for example, the JVM or the .NET Common Language Runtime, the CLR, you can build new languages on top of those virtual machines, on top of those runtimes. So you can invent Kotlin, you can invent F#, whatever you want, because you have a runtime that understands how to take the high-level stuff and turn it into native, fast, low-level stuff. That doesn't exist with JavaScript. You just have to represent your code as JavaScript. Now, we've been writing code that isn't JavaScript alongside our JavaScript code for the last quarter century, and there's a pretty huge gulf between those two things, right? So that sucks. It's time for a better way. And that way is WebAssembly. And what I'd like to talk to you about today is the nature and the patterns that WebAssembly can provide that are of interest to, I think, people who are developers, but also people who run, manage, and build application portfolios. So you might be looking at some enterprise legacy portfolio with 1,000 applications in there. You know, some of that's really crufty old stuff. There actually might be a use case for WebAssembly for some of those things. So we'll talk about that. So we talked a little bit about the story today, about how we got up to this point. And I'd like to talk a little bit about what WebAssembly actually is. So how many of you have heard of WebAssembly? I mean, you know, besides to whatever extent brought you into this talk, the word WebAssembly is in the name. But how many of you have heard how many of you feel like you could describe WebAssembly in 1 or 2 sentences? Okay, so a lot of people have heard of it, maybe not a lot of people get it. Okay, cool, great, welcome to this talk. So if you look at the WebAssembly specification, there's the opening couple of paragraphs, I think, provide a lot of insight and are very densely packed with some details that we'll dive into in terms of why WebAssembly and how WebAssembly might be a good fit for certain kinds of applications. So I think the first interesting thing is that WebAssembly is a code format, right? So when you look at the specification, you can see that it says very explicitly, there's basically these 2 formats, binary and text. So when you want to write WebAssembly, you're going to represent that in one of 2 ways. A WebAssembly text format, which is the WAT or WAT format, and the WebAssembly binary format, which is the WASM or WASM format. So I say WASM, sometimes people say WASM or whatever, but same idea. So the WAT and WASM files are the representations of WebAssembly, the different kinds of representations of WebAssembly that you might have. WAT is more human readable, so it has symbols that are of strings and things like that, and WASM is just straight up binary. It looks like assembly, you can't read it. If you're a human, you have to get some kind of interpreter or something. So let's take a look at let's just look at what a sort of hello world example of this might look like. And so I'm going to pull up what is a REPL for WebAssembly, which you can look at yourself, called WASMFiddle. And on the left here, I've just written a really, I'll make this maybe 1 size bigger for folks in the back. Oh, nope, that's too big. On the left, I've written here just a really simple C function, right? All this function does is return the integer value 42. And what I'd like to do is have that C code run in a browser. Right, so that's the promise of WebAssembly. I should be able to take something that wasn't designed for the web, right? You don't see anything here about the DOM or loading stuff into memory or anything like that. You just have a function that's naked and returns an integer value, right? How can I get that code that I wrote that wasn't designed for the web, that doesn't have anything to do with JavaScript really, and how can I use that code to do something interesting in JavaScript, to do something interesting in a browser? So the point of WebAssembly is I should be able to take the thing on the left and put it into my browser and have it work. So the way that happens is in a few stages. So the first thing is that my language, the way that I write that code, has to have WebAssembly as a target. Just like if I wanted to compile a game for the Nintendo Switch or target the PlayStation or whatever, I would need some tool chain that targets that architecture. Or if I want to target x86 versus 64-bit processors, right? I need to target that architecture. So we'll talk more about what that looks like. But that's as long as there's some way to target WebAssembly as a target, you can. It doesn't matter what language it is. We just need to be able to represent it as WebAssembly. All right. So I'm going to. So I'm going to build this, and you can see a few interesting things pop up. So on the bottom right here, this is the text format, right? Remember how I said there was a binary format and a text format? This is the WAT. This is the WebAssembly text format. And you can see here maybe you don't know anything about WebAssembly, but you can kind of guess what this does just by reading the text format. You can see that there's a function called main. It returns a result of type integer 32, and I'm going to respond with a value of type integer 32. It's a constant that equals 42. Right, I mean, there's some other stuff here about memory, and that's not important for our purposes. But basically, there's a bunch of setup stuff that happens, then there's a bunch of stuff that we wrote, and I mean, that's our WebAssembly, right? So at that point, and if I look at the binary format, this won't be. I'm not going to show you the binary format. That's not very interesting. You're not going to be able to read it anyway. So I've got my WebAssembly blob. I've got a blob of stuff that represents that code that I wrote. That's cool. It's not in a browser yet, right? So what I'm going to do is take the code that I wrote on the left, and if I'm in a browser that supports WebAssembly, which is basically every current modern browser at this point, so Firefox, Chrome, Edge, they all support WebAssembly, you have a new object in your DOM called WebAssembly dot a whole bunch of stuff. The interesting one is WebAssembly.module and WebAssembly.instance. So WebAssembly.module says, I would like to make a WebAssembly module, a sort of sandboxed piece of code that represents the file that's on the left here. And then I'd like to run all of the export. I want to get all of the things that code exports and makes available to me, and then bring them into my environment. So you can see here that one of the very interesting lines is that this exports the function main, right? So I could have other functions in here that also get exported. So for example, let's say that I just add another function like int, int 3, and I'll return the value 3, or I don't want to return 4, that would be a bug. So I'm going to build this again. You can see a new function is now added to the list of functions we know about from this export and will be imported into our environment. So now I can use the value of that function from the exports that were in the instance that I loaded. So for example, I could say, hey, every time I run, I want you to print this value I want you to log that value to the command line. So I'll run this. Cool, I'm returning the result 42. If I wanted to use a different function, I can say, all right, I want to use 3. Cool, I'm returning 3, right? So the point of this, that's obviously a very straightforward example, but you can imagine that there's anything is on the left, right? Not something that returns the value 3 all the time, but something that, say, takes a textured image and does some very expensive mathematical transformation to it, like shading a bunch of pixels, or maybe it turns a document that you have into a PDF and renders it entirely inside your client, et cetera, et cetera. So imagine any computationally intensive piece of work happening inside of your browser instead of on a server and shipping all that traffic back and forth to you. Imagine instead just shipping the code to where it's going to run and then running it there. So that's I think, the essential promise of WebAssembly, is being able to do things that were previously expensive that might have had to occur server-side directly in the browser. So I think that's very exciting from a number of different perspectives. Okay, so let's switch back to, there we go. So the next part, so it's safe. What does safe mean? Safe means that WebAssembly is not subject to certain kinds of runtime errors. So for example, we were using C before, right? C is notorious for having buffer overruns. In fact, this is a major class of exploit that if you discover a buffer overrun somewhere, you can reliably inject somebody else's malicious code into the part of the buffer that runs past the actual allocation for your memory, right? So WebAssembly, as we'll see later, WebAssembly enforces certain kinds of patterns that are not possible to occur in an environment that otherwise would have been possible. So for example, WebAssembly's memory representation is just a single array of fixed size of memory, and you have to choose which slices of that memory you're getting. So you can still have a buffer overflow in your C code, but that buffer is going to overflow inside of the WebAssembly sandbox, which means that it can't overflow into, say, the browser or into any code that you actually care about. So the rest of that process is sandboxed from whatever would have happened inside the WebAssembly stack machine. So because it's its own execution environment, that's really powerful. It's sandboxed just like your JavaScript code is. So it's not subject to things that couldn't have otherwise occurred outside the sandbox. So I think that's really powerful because it means it takes away a class of exploits that otherwise would have been vulnerable. You know, maybe people feel a little nervous about running C code in a client, but this takes away some of the possible danger zones. Now, it doesn't take away everything, right? So you should still have race conditions. You can still have all kinds of other problems, but it does make a class of programs that might have otherwise been dicey and remove them from being a problem. So WebAssembly is portable, right? Because every browser that supports WebAssembly is one that's running the WebAssembly specified stack machine. That means that every one of those browsers, doesn't matter where as long as you targeted WebAssembly, it doesn't matter how you built that or what language you used to build that. It will run your WebAssembly module the same in Chrome as it does in Firefox. So because that stack machine implementation is the same, the low-level implementation is the same, you're going to have a consistent experience no matter how you run or deploy that WebAssembly application. Because it's a low-level code format, again, you're not dealing with some of the vagaries of maybe differences in implementations between, say, a JavaScript engine over here and a JavaScript engine over here. They can both run JavaScript, but they can't have they won't have the same low-level representation of their code. So certain numerical operations might perform way better in Chrome than in Firefox, for example, because they're using different numerical operations for running JavaScript. But in WebAssembly, that execution is happening at the same low-level virtual machine side of things. So that means that the way that that code runs is going to be a lot more consistent from browser to browser. The WebAssembly is also specifically designed for being efficient in execution. So it's not just efficient in terms of its representation, it's also efficient in terms of its execution. What does that mean? So when I made that call to go grab the WebAssembly module and download it from somewhere and put it into my environment, that download happened in a streaming basis. That means if I have a huge WebAssembly module, I can actually start executing before I have finished downloading the whole file, because those exports come first along with the declarations of what happened. So I know already that I have a function named main and a function named 3 before I actually know what main and 3 do. So I can continue asynchronously in the background loading the rest of my code, and I don't have to wait for main and 3 to show up until I actually call main and 3 somewhere else in that execution, right? So I can keep downloading in the background, I can keep executing JavaScript. It might be a while before I actually call one of those methods that's in WebAssembly. So I can download that file and keep executing. I don't have to block on the other stuff that I'm doing unless and until I start invoking something that's inside the WebAssembly module. And even then, once I've downloaded that part of the WebAssembly module, I still don't have to wait, right? Like if I've downloaded main, but I haven't seen 3 yet, and I call main, I'm good, right? I don't need anything else. I haven't called 3 yet, so I don't need that. And then finally, the compact representation is a big win, right? So we saw that binary representation of all the C stuff showing up in a way that was fairly compact. So I exported what it means to return 42 into a binary blob, and that's very specific, very structured to the way WebAssembly works. So those exports that we saw before, that interface is really, this interface here is really defined by the exports. And the memory block I talked about before, that's also an export. So I can actually directly access the memory that's being used in WebAssembly as its own separate object. But each of these export lines defines the entire interface that's exported by WebAssembly. If I deleted the 3 export, it would not be available for calling over here. I would just get an error that says, hey, I don't see a function called 3. There's nothing that's been exported. So so as we saw before, the behavioral representation of WebAssembly is fairly compact, and that means that the way that I use WebAssembly in a structured environment, like when I'm using my browser and I'm downloading WebAssembly and I'm running it in my browser, it's much less of a concern about what the scope of what could happen here is. If you open a minified JavaScript file, you could see thousands of lines if you have no idea what could be called at any given point or what the sort of totality of that interface is. With WebAssembly, that representation is explicit, and it's very specific about what is or isn't included. Okay, so what's it good for? What are the kinds of use cases that you should care about with respect to WebAssembly? So I don't have time to go into everything, but here are some use cases that I'm already seeing with my clients that I think you might be interested in too. So we alluded before to sort of computationally intensive workloads, things that might be expensive to run on a server. So you probably don't want people doing things like rendering huge textures on a server and then shipping those results back to a client. That's probably something that can happen on the client side. So anytime you're doing something that's numerically intensive, rendering images, doing a lot of calculations, batch processing on a huge file, that can probably happen on the client side. You probably don't have to ship a bunch of stuff to the server, wait for the results, and then ship them back to the client. So that's been a big use case for a lot of my financial services and insurance clients. A very common thing is that you upload some very big, important file to the server to do something. The server churns for a while, and then you get something back. So you're sort of transmitting a bunch of information, waiting for that upload, waiting for that processing, waiting for the download result, when you could have just maybe run that code locally and save yourself the whole network I/O step. And especially when these files are dozens of megabytes or maybe even gigabytes, the thing you're waiting for is really the network I/O, not the CPU. So if you can cut out the network I/O, you've saved a huge amount of time. So if you have cases like that where you can trust the client or you're running maybe an internal application, that can be a really good use case for WebAssembly. The second kind of use case is for more public-facing stuff. If you have general purpose workloads that are public-facing that would be advantageous to run on a client, that's another good case for WebAssembly. So a classic example would be like, this is a literal example, would be something like you have a PDF that you want to render. Instead, maybe you add a watermark to it and people go to your site that, maybe they go to Kindle and they look at their books and they want to download that book as a PDF, right? Maybe Amazon doesn't want you sharing that PDF with everybody, so they watermark it. So that's the kind of thing that could happen on WebAssembly. So there literally is a PDF JavaScript library that currently was at one point implemented in JavaScript called PDF-TKJS. That is now running it's now a WebAssembly module, because it's a lot more efficient to run that as WebAssembly than it is to run that in JavaScript. And the third use case that you might care about is when you have things that are not just numerically intensive and not just client-facing, but are also sort of one step in a chain. So for example, maybe you have a microservice that you want to deploy to, or that you want to send some information to, and you have to send that workload out many times over. So if you're doing something in a very repetitive way, or if you're doing something with the same piece of information to a lot of different services, it's probably better if that happens on a client side where that control can be managed a little bit better, instead of replicating it out once in every microservice on a server-side approach. So those are the 3 biggest use cases I've seen. That's what WebAssembly addresses today. In the future, I expect that as the WebAssembly capability set grows, we'll be able to do more more expanded set of use cases. So for example, one of the things that WebAssembly doesn't support very well is garbage collection. So if you have a garbage collected language, there's not really a way to represent that easily in WebAssembly. So you can't really have Java and then turn that into WebAssembly stuff. It works, but it doesn't work well because the garbage collection instructions have to be implemented at the WebAssembly level, and it's not optimized for that very well. So I expect that use case will get bigger, that set of use cases will get bigger in the future. Today, though, you don't actually want to write WebAssembly, right? You don't write WAT, you don't write WASM, you write something else and you compile that to a target. Now, that means that you have to have languages that support that. Right now, WebAssembly's basic data types are just int32, int64, float32, float64, and that's it. There's no strings, there's no arrays, there's no pointers, there's no hashes, there's none of that. So you have to have, and that's why the numerically oriented side of it is important. It has to really be aligned to doing a lot of work on a large amount of data repetitively. So if you don't have data that looks like that, if you don't have applications that work on large amounts of numbers, WebAssembly is not going to be a good fit. The second is that the debugging facilities for WebAssembly are not super great right now. So if you have a language and you wrote something in C, I compile that to WAT or WASM, great, now I have this binary blob. If that binary blob throws an exception, I can't really see into where in the binary blob that happened. I just see that at this byte index, something bad occurred. Okay, that's great, but I need some kind of tooling that's going to support that. So right now, that tooling is not very good. The debugging facilities are not very good. The source map capabilities for WebAssembly are not as good as they could be. So they exist, but if I look at JavaScript or CSS today, I have really good source map capabilities for my browser. I don't necessarily have all those capabilities for WebAssembly today. Now, if I'm interested in using WebAssembly, there's a few places that I could start. So one is that just to sort of give you that architecture before, you have something that turns what you wrote into WebAssembly, and then that thing is running in a stack machine in your browser. The tools that look like that are things like Clang, LLVM, and Inscription. I've included some links here in the PDF for the slides that'll be interesting for you, but there's a couple of places I want to highlight specifically. So that's the way that you get to WebAssembly can happen in a number of different approaches, but the binary toolkit for WABT is one way to just start playing around with WebAssembly directly. So if you want to literally type in assembly instructions and play around with that text format and have it turn into something that you can build a module with, that's how the WebAssembly binary toolkit can help you. If you want to play around with the REPL, like I was showing you before, that's WASM Explorer. If you want to just have fun and look at some of the consumer-oriented use cases that people are doing with WebAssembly today, that's awesome WASM. So those are the three places I'd get started with for WebAssembly. So what's next? What should you care about in the future? So remember, WebAssembly is not a replacement for JavaScript. It complements the use of JS runtimes, but if you're using JavaScript today, it doesn't make sense to undo all of that work and rewrite it in a different language that targets WebAssembly. It works right now, so keep using JavaScript. So it's just that sometimes you want to run code that JavaScript's not very good at running, and that's what WebAssembly is for. So you don't target JavaScript for those things, you target WebAssembly. There's nothing really special about WebAssembly. It's just a binary blob that runs in your browser, right? So anything that you would run on Pivotal Platform today that you're interested in experimenting with WebAssembly for, you can do that with WebAssembly, right? There's nothing special about some web application that targets WebAssembly. It's still just another web application. So if it's Java running in Tomcat, great. And from the Pivotal Platform perspective, that's just another blob that's in your static files directory. It's here, it's today, it works in browsers right now today. You can do those things that I just showed you, but I don't think it's mainstream and it won't be mainstream for a while. But there are specialized applications showing up, and I think it is important to keep this in mind as a technology, right? In 2013, 2 weeks after Docker was announced, I was supposed to give a conference talk at a conference called SpreeConf, which is about e-commerce applications. And I was supposed to be talking about this AWS technology, but it just come out that was sort of like Beanstalk. But when I saw Solomon Hykes' talk, I was like, wow, people need to know about what Docker is, even though all that exists is a 5-minute lightning talk and this terrible binary that doesn't really work. That's how I feel about WebAssembly today. I think that it's in its very early stages, but it's something we should all be paying attention to because in 5 years it's going to be a lot more important than it is right now. So thanks very much for your time. If you have questions, I'd be happy to take them on my Twitter account, or you're welcome to stick around or email me. Thanks very much for your time.